So welcome. So I'm going to talk to you a little bit about what Capital One's been doing with data streaming. So first of all, I'm a principal software engineer and solution architect at Capital One. I've been there for 16 years. I did go through the SEI's software engineering program and have a certificate from there. And I lead a team within what we call our chassis framework that works on a number of different solutions, including a framework for internal development of applications that supports over 100 different agile teams. And one aspect of what we do is data streaming solutions for all the applications that are using our framework. And then, of course, I'm sure most of you know Capital One, but for those that don't, we're a large, diversified financial services company, but also a technology company. And so we have invested heavily in our technology solutions to help us kind of grow our business. Because we think that that's where the future is, because of the explosion of processing capability that's available on mobile devices and out in the world. All right, so I'd like to start with this kind of statement. Big data, so we're all familiar with big data. Big data does not equal big insight, but it is a prerequisite, right? So you can't get those big insights that management wants without having a lot of data on which to base your assessments. And so just some facts that I've garnered out there kind of give you a sense of how much this is. So Facebook collecting over 500 terabytes of data a day. Google processing almost 6 billion queries a day. Amazon estimated to have more than an exabyte of data. That's like almost enough books to reach the moon. And then Capital One ourselves, probably much smaller than these folks, but 3 petabytes of data in our data lake and growing at a pretty significant rate. So why are all these people doing this? Why are these companies collecting all that? And that's because getting this data gives you the ability to mine that data and find within large data sets these little nuggets of insight, right? So that you can find these little opportunities to better serve your customers and to improve upon the marketing, as well as to reduce costs, find patterns of customer behavior, et cetera, right? So why so much? Well, predictive analytics requires a lot of data. Statistical models require something that gives them statistical predictability and convergence, right? And so you need that large set of data. So how are we applying that large set of data? So I'm just going to show you 2 of a large number of visualizations and dashboards. This particular one comes out of a tool called Tableau, which is showing attempts to log into various Capital One servicing centers and how many customers, as you can see here on the upper hand side, do that within a single attempt, multiple attempts, or did not complete. And obviously what we're trying to do is assess from that, well, what's going on with customers? Was it a servicing outage? And down here you see call centers. So we're trying to basically determine, is the number of people who can't log in successfully driving call center volume, because call center volume drives cost. Here's another dashboard coming out of Splunk, which is, we call this Genesis. And we're collecting a large amount of data out of our APIs and applications and feeding that in here, and then we're running some predictive modeling software underneath it, and we're generating some interesting scores, one that we call Slick. Not sure what it actually stands for, but essentially it has been shown to statistically predict the likelihood that we're going to have some sort of a customer impacting event within our environment. And so by monitoring that Slick score and attaching monitors to it and alerts, we can actually go in and look at what's going on in the environment and attempt to avert an incoming scenario. So when we see a trend that maybe isn't particularly obvious, but a downward trend here, we'll see the Slick score start to go up. And we can actually start going out and looking at the environment and figure out what's going on so that we don't have a disruptive event for our customers. All right, so I'm going to show you where we started. And then hopefully with enough time, we'll get to where we are now, and I'll talk a little bit about where we're going. So I'll bet that this looks really familiar to everybody in this room, or most everyone in this room, right? So everyone has whole bunches of different applications that are producing data. Some of them are writing it to log files, and you're pulling those into Splunk with Splunk agents, or you're using batch processing tools to grab those files and perform traditional batch ETL processes. You're sucking data out of your vendor systems, your systems of record, and all of that is finding its way through ETL processes back into these big data warehouses, right? You also may have apps basically dumping data out on messaging queues and separate apps collecting that out, throwing it in central databases, and also being ETL'd out. This is what we looked like. We had a central database where our internal framework made it really easy for application teams to log data out. At the time we were using ActiveMQ. And then we were basically pulling that data off these queues to decouple the applications from the data sinks, and we were streaming all this data back into this repository. And then we were feeding back into these ETLs, and that drove all of our reporting. All right, very, very common. But why did we say this was terrible and we had to blow it up? Well, it was great for the time, terrible for now. Well, here's what we saw. The demand within the business for data was growing at an exponential rate and then starting to level out. They were asking for lots more data, and we made it easy to collect that data, right? So what we saw was that that central database was growing by 450 gigabytes a day and climbing. So we had to scale it, right? So 2 databases, 1 per data center, went to 5 per data center or 10 databases. There's a lot of cost there. And then it made it hard to extract and merge all that data together and create unique keys to it. And then we were logging 450 gigabytes a day, but 80% of that data, the backend analytics team said, is noise. They didn't want it, which meant that we had over 300 gigabytes of data that was noise. Right? The other trend we saw was that the business and the decision makers basically were saying, hey, we used to be kind of nightly, and that was good enough, but we want it essentially instantaneously. That's what they're presenting to us. Now, everyone goes, is this supposed to be there? And yeah, we actually saw a little bit of an uptick where they said, we're willing to wait a little bit longer because we understand you're building some architecture for us, right? But really quickly, they said, deliver data now, deliver it quickly, all right? So what they wanted was the desire to react immediately, as quickly as possible, and then move from reacting to predicting. So putting the thing in front of you before you even know that that's the thing you wanted. So what were the guiding principles that led to our evolution in this architecture for the streaming solution? One was that we decided all data should go to Hadoop. That was going to be the central lake. We wanted to standardize on open source software, all right, avoid vendor-based systems. We wanted to centralize the access to the data lake so we had a strong point of control and so that we could control access to the lake so not everyone could get at that data. Capital One embraces the public cloud. And so last year at Amazon's big conference, we announced that we were moving almost everything into the Amazon cloud, and I'll talk a little bit about what that means. Obviously, being a bank, we obsess over security. So we really want to understand the implications of both being in the cloud as well as streaming all this data back, because we, like all credit card issuers, are subject to payment card industry DSS standards, which means we have to encrypt certain types of data and provide certain types of controls. And so that was a front and center requirement. We wanted to eliminate vendor-based relational databases and reduce our reliance on data warehouses, because with the data lake and some of the more modern tools, you really don't need them. You get much better capability. I don't know if anybody attended the session yesterday on Scala and Spark. Amazing power in 5 lines of code, right? And then, of course, adopt big data tooling. Okay, so how do we select our data streaming tool? What's that architecture look like? So the idea was to take all of our applications, both internal associate-facing as well as external customer and consumer-facing, across web apps, mobile apps, tablet apps, everything that we put out there. And we wanted to provide easy mechanisms to ingest that data, whether the applications were talking to an orchestration layer or whether they were talking directly back. So think clickstream logging, user activity logging coming directly off the mobile devices via APIs or direct to this framework, as well as back-end applications. We basically wanted to centralize access to Hadoop, right? And then we would let all of the legacy ETL processes hang off of Hadoop. And that way, we could eventually migrate customers' reporting analytics to using Hadoop and the tools sitting on top of Hadoop like Hive, and eventually get rid of these everywhere we could. And so we made some decisions to centralize on a data streaming technology, drive all the data through it, and then push the data into the data lake by using Kafka as our input, and Flume is the mechanism to write it in. That way we have a clear boundary between applications, streaming, and entry to the lake. That way no one gets access to the lake unless they should have access. And Flume gives us the ability to control how data comes into the lake. Right? So here we use Flume to register data sets and data set instances into the lake on a regular period. Okay? Is anyone else implementing a technology similar to this? Okay, we got 1, 2. That's actually pretty good. All right, so we selected at the time Spring Extreme Data. So Spring Extreme Data is built on top of Java and Spring, and it uses both Spring integration and Spring Batch. So it's reference implementations for those, and it's a very modular implementation. So why did we pick that? Well, there were two sets of factors that we used in the assessment of different solutions and the selection of that aspect, this piece, the green, in our architecture. First of all, we were looking for something that was open source and that we can contribute to, meaning that our developers could submit pull requests to them for things that we wanted enhanced or extended. We are largely a Java and a Spring shop, so we were looking for something that had those same technologies. And we were looking for something that had a significant amount of productivity boost. And Spring Stream Data came with out-of-the-box implementations of modules that gave us connectivity to all the sources and sinks that we were using within our environment. So they have HDFS, Avro, Parquet, HTTP, RabbitMQ, JMS, File, Mongo, basically everything we wanted, plus some other kind of features, the ability to do filters, splitters, implement a predictive modeling markup language or statistical model directly in Stream. The other thing we wanted on the architectural side was the ability to scale the application. And we were looking for both vertical scale as well as horizontal scale. Now, because we're in the AWS Cloud, we can select our instance types. And so we can basically select compute optimized or RAM optimized or whatever. But we wanted something where when we picked something, we could fill it up as much as we wanted or reduce it down to run at the right kind of CPU and memory profile. We also wanted the ability to scale it horizontally, right? So when we were doing our testing, we were getting about 2,800 TPS through kind of our initial testing per instance, per physical node that we stood up. We wanted something that was modular so that we could assemble solutions from a set of simple components. And those modules that they provide made it easy to do that. I'm going to show you an example of what that looks like. We wanted something that was both extensible and shareable so that we can create custom modules and that we could extend the capability within the modules they provided for our own particular needs. And we actually had to do this with the Mongo Sync, where the Mongo Sync did not support a revolving master replica set, where the master could basically revolve amongst the cluster. And so we had to extend their out-of-the-box Mongo Sync to provide that capability. And then we issued a PR back to Pivotal for the merge. We wanted a lot of options for deployment. I'll show you what some of those look like. And we wanted to be able to interoperate freely between batch and real time. So we have a lot of use cases where there's a file that may contain 50 or 100,000 records that we need to do something with. For example, send a message or an email to a bunch of customers that says, hey, your payment's due. We like to do that. So we wanted to be able to kind of get those batch files out, but then run them through the process in real time. So it provided a lot of these useful constructs. It also provided some other interesting constructs I'm going to talk about. One is the concept of a tap. And so this turned the data stream from a series of modules that went A to B to C to D, so source, process, sync, to source, pub, sub, multiple processing streams. So essentially, you could take every data element coming through the front door, and you could create a tap, which would create a duplicate flow of that data through an alternate process. This proved extremely useful for us, where we wanted all of our observations to go to the data lake, but we also wanted 90 days worth of data to be in Splunk, because that's what our production support team wanted. And then our data scientists would show up and say, hey, we're playing around with Elasticsearch and Kibana. Is there any way you could give us a feed of production data for the next 30 days? And we're like, oh yeah. We would just tap existing production streams and drive it right over to Elk. So we had a lot of ability to kind of send the data to multiple locations. But then each one of those locations we could attach filters to or custom processing modules. We could do data augmentation on it. So essentially the incoming raw data, we could send it all to the data lake raw, but we could also tap it over, augment it with customer data or other observations, send that to Mongo or send it to Splunk. And so it gave us that centralized solution that gave us many ways out to many different syncs. Okay? And then we also wanted to be able to do things like stream analytics. And so I include just a little simple snapshot down here of what that looks like. So we can essentially tap the data, and they provide these real-time analytics where you can look at the message, and you can basically count on anything. And so you can do aggregate counters based on, in this particular example, we're showing just something simple like IP address. But you could use this for like geolocation. Where are my customers coming through? Where is the highest incidence of payments? Is it in urban centers? Is it rural? And so you can get those directly in the tool as the data is flowing through, and they're constantly updated. So here's kind of what the solution looks like now. Applications are sending data into us. Largely, they're coming in through AMQP to RabbitMQ. And we like that because it decouples the application. But we have some that are using kind of standard HTTP request response. Note, I didn't say REST, HTTP request response. But we also have some where they're doing JMS or other different types of inbound. And so we're setting up processing streams that consist of source and sink modules, where they come in, we read off Rabbit, we do some custom processing, we may call external APIs to augment with customer data before we send that down to the Kafka cluster. We're also tapping data off to Splunk to build that dashboard I showed you right in the early part of the presentation. And we're also tapping to produce inline metrics. We also have reprocessing queues. So the way these streams are built, they'll try to deliver, and if they can't, they go to a dead letter queue. And then the dead letter queue, we set up reprocessing queues that will try to reprocess it through. And if that fails, we'll dump it off to a file so that we can tell the business we're highly reliable, that we won't lose your data, which is really important with audit data. Okay? We can also do filters and taps to other data sinks. So some of our key decisions, we standardize in JSON as a structure. We use RabbitMQ to decouple. Our primary data stream would be to HDFS, and the taps would be from there to Kafka and other places. And then once within HDFS, we could use Hive, MapReduce, and other tooling there. And then, like I said, these reprocessing queues. Now, don't get scared by this. I know a lot of us are architects, but this is some simple DSL, or domain-specific language. This is how easy it is to define a data stream. So in this top example, stream create, I just provide the name of it. The definition, and this is the heart of it. This says use the Rabbit module, ingest from this queue, and send it to Kafka on this topic, on this set of brokers. Now, you'll notice localhost in there. Hold that in the back of your head. I'm going to come back to why it says localhost in a minute. Thank you. All right, so here's an example of how we do this. And these taps just basically say, hey, tap this stream. So for every event coming through this stream, I want you to tap it and send it to Rabbit, where another stream is going to read it and send it to Splunk. Right? Another thing is this ability to do deployment properties. So when you deploy a stream, it's going to pick one node within the cluster to put each module on. But if you want, for example, to have HTTP behind a load balancer, you need that HTTP source on all the modules. And this gives us the ability to do that. All right. So now I alluded to the fact Capital One was moving into the cloud. So we're in the AWS Cloud. And so there's some implications to being in the cloud. So we had to basically build automated provisioners to build these environments. So we can literally spin up this complete environment in 10 minutes or less within the AWS Cloud. Now, one of the things we found with SpringXD was that it does, within its configuration, use some static IP addresses. And that meant that we couldn't use AWS's auto-scaling groups. So for example, the Zookeeper Ensemble IP addresses and some others. So we had to do what we've always done as architects, understand capacity and provision a fixed-size cluster. And then we periodically tear these things down. So every 60 days, we completely tear down production and reprovision it. We're putting these things behind ELBs. We're using CNAMEs to hide the customers from the IP addresses. And then we're basically creating integration and strong security around LDAP. And then we're using a host of different tools, including AWS native things, JMX and Zabbix, to monitor the environment to understand how much data is flowing through it, and if the environment is just up and reliable and running. And if there are any issues, we're getting automatically triggered alerts. So here's what we look like in production. We have many producers coming through these availability zones. Now, we are deploying this solution across 3 availability zones. Okay, so the reason we're doing that is to protect us from data failures. So if there's an availability zone loss, we still have 2 availability zones running. We also get the ability to do green-blue deployments. So when we release version 3, we can deploy it by taking this section out of rotation, removing it from the ELBs, deploy the new code in here. All right, then we can bring that into rotation, take this one out, and so essentially we get a very safe migration path. All right, and then we have these ELBs with CNAMEs so that we can protect the consumer from changes. We can also point them at these internal ELBs if we just want to, for example, do a beta deployment and say, hey, you want to test new beta capability, you're only going to be here. Don't talk to this ELB, talk to this ELB. There were some challenges that I alluded to, and these are the top 3 that we had. The static use of IP addresses. So here we had to allocate fixed size clusters, no auto-scaling groups, and do proactive capacity allocation. Real-time monitoring, we had to enable a lot of metrics, a lot of JMX data streams, which, by the way, our JMX data comes out through Rabbit, and we use the actual environment itself with a data stream to stream that data off to Splunk. So we're actually eating our own dog food on this. And then we're using the deployment counts on modules to kind of control how we scale both horizontally and vertically within the containers. If I had more time, I would show you like what this looks like in the actual administration tools. Security considerations. So remember about 6 or 7 slides back, I showed you a stream definition we were writing to Kafka, and all of the broker IP addresses said localhost. So why are we doing that? Well, because we're in the AWS Cloud, we wanted to be really, really tight on security. And Kafka at the time did not have an implementation that supported secure transport. So all the data going into Kafka was in the open, and that wasn't going to work for us. So what we're doing is using a tool called STunnel, which is a low-level utility that creates an end-to-end secure pipe between an agent and a remote. And you provide a certificate file that will encrypt the data when it comes in. It will stream it out and come out. And so what you do is you assign a local intercept port, let's say 1,000, and then it writes to 2,000, streams to the remote on 2,000, which then goes back out to 1,000. So Kafka is running on a particular port, and STunnel is running on a particular port, and it's using a separate port for that secure pipe. And so this kind of shows you kind of what that looks like. So this gives us the ability to transmit data over a AES 256-based encrypted pipe between AWS, the actual instance where the data is in memory, all the way back to our Kafka cluster using really strong encryption. And so the way that looks in the stream definition is that writing to Kafka localhost. So it thinks Kafka's local. But it's actually writing to the STunnel agent, and then STunnel's encrypting it, sending it, the other agent's pulling it back off, and then it in turn is adding it back onto the Kafka node when it reaches it. So this was a really interesting solution that our enterprise data services team came up with for us to use, and we've actually used this in a few other places now. For example, securely communicating with DB2 on the mainframe from AWS, we're using STunnel to encrypt that data. The other thing we did was we used the collection of credentials. We encrypt those, and we use Chef to provision our environments, and we're using a construct called an encrypted data bag. So a data bag is just a collection of data, but we encrypt that data using a symmetric shared key. So the key is collected by the user when he initiates the build job. It's used strictly in memory to encrypt the data bag. The data bag then goes to the Chef server and gets pulled down onto the environment by Chef, which then contains the credentials, such as database user IDs, database passwords, et cetera. And we're also looking at a tool from a company called Hashi. All right, so Hashi provides some things like Terraform, which is a tool that we also use for provisioning AWS, but they provide a tool called Vault, which is essentially a credential store. And so we're looking at building a custom integration adapter for Spring XD to talk to Vault. And so we will securely connect to Vault, and we'll source things like certificates, PEM files, connection credentials, user IDs, and passwords out of Vault so that we can essentially manage them with Vault. And then eventually we'll be able to deprecate this encrypted data bag. All right, so the last thing I'm going to talk about briefly is what our, because it wouldn't be, the SATURN if I didn't show some UML, right? So within our chassis framework, we have a couple libraries. One is called Data Framework Service, and the core of that library was one I wrote. And so the concept here is that we have some interfaces that define what we call a stream emitter, which is basically within your app, it's the thing that's going to emit data and stream it out of your application. And so we might have an implementation, for example, that's AMQP stream emitter. That's writing to Rabbit. We could also have an HTTP stream emitter, whatever type of emitter you want. And because our framework is extensible and we're on a fork and pull model, application teams can show up and say, hey, I want to build XYZ emitter. And we go, great, just extend off this interface. And then we provide off of that the ability to attach client-side data filters. So if they know there's X amount of data coming out and most of that data is unusable, they can filter it before it ever gets streamed out. We can also filter within the streaming environment, but we tell them, hey, if you know we don't need it, filter it out here. And then each emitter can have a transformer and an entry point. So entry point represents how it gets out, and the transformer represents how I take the raw Java objects and turn them into a representation. So for Spring, we're using Jackson to transform to JSON. We've also played around with some different encoding formats, but it's all an extensible framework. And then here's a chunk of code. So we're using Spring-based annotations, and this is all an application team has to do to get their data out. They add an annotation that says, send out the account ID, and it automatically will get streamed out. Or annotate a method with event stream, and then they provide some additional, and I've given a very complex example here to show how extensible it is. So they have a standard stream, which says, hey, I go to log file if I can't stream it out. If my RabbitMQ points are unavailable or HTTP comes back with a 400, then it'll write to a log file so I don't lose it. But here I'm going out via a custom event stream called audit to this audit emitter, and that audit emitter is the emitter I showed on the previous UML. And so application teams can very quickly annotate their code to stream all kinds of data out really, really quickly. And they can even do it in a way by saying, hey, I want to stream this out, but it's non-public information, which means apply encryption to it before it gets streamed out. All right, well, thank you very much. If you want to see a little bit more about our journey, I think the slides are all going to be posted, right? Yeah. So this is the presentation I did at the Spring One conference, which has got a lot more detail about Spring Extreme Data and some of the infrastructure. And you can also, I'll have a blog up on CapitalOne.io called Turning Data into Insights. So if you're interested in some of the things Capital One's doing with engineering, you can look at Capital One's engineering blog out on CapitalOne.io. And like many other companies, we're looking for talent. So thank you very much. Topic. Yep, yeah, that's just the topic. And that's meant to show that we have specific data streams that are talking to specific topics. So for example, all of our customer sign-in and multi-factor authentication comes into a specific topic. Credit decisioning stuff would be in a separate topic. And that's just so they can kind of keep the data segregated. So they have different users subscribe to those different topics. Yeah.
With your kind of attribute, the quality attribute that you need to security all the way through, how do you guys achieve that? When I envision Flume, I think of a centralized Flume cluster doing data movement from Kafka to HDFS versus, say, LinkedIn, various Goblin and what have you.
Yeah. Yeah, so the question was really about Flume in the architecture and how you kind of maintain some security there. So what they've basically done is set up kind of a separate security zone within our network, and all of the HDFS data lake and everything sits within there. And so within HDFS, all of the data nodes themselves are unreachable by anybody except the EDS specific team. And then Flume is the only one that's on the edge nodes that has the Kerberos-based security to actually connect to the lake. So the only way in is to either be one of the blessed few who have the ability to get to, or to come through Flume. So then they basically lock down Flume and they say, okay, now Flume can only connect to these Kafka brokers, right? And so the front door becomes Kafka. I don't know if that's maybe not as rich an answer as you'd want, but it's...
I've got some questions. I'll follow up on that.
Okay. Yes, yes, sir.
Actually, first, I have a Capital One credit card.
Good for you.
After this talk, I feel much more secure, so thank you.
Hey, you're welcome.
So a question I had was, does your system support multi-tenancy? Does it even make sense for you guys to support multi-tenancy?
So tell me what you mean by multi-tenancy so I can give you the right answer.
Well, I mean, do you allow multiple entities, separate entities, business entities, maybe within Capital One to be a customer in the system?
Yes.
They can separate their data, they separate their identity,
Yep.
things like that.
Yep, and so the answer is yes and yes with a caveat. So the caveat is that this centralized streaming environment we set up, and when we looked at the overall amount of data that was going to be collected across all the lines of business, we decided that we wanted to create separate environments for card, the card division, from, for example, commercial, which is really low volumes. And so commercial said, I don't want to compete with card. And card said, I don't want commercial, I'm just using commercial as an example, so when commercial watches this, don't come and hunt me down. They said, I don't want commercial's bad coding practices to destabilize my environment. But within the card ecosystem, we have our partnerships business, our originations business, our servicing business, all kind of coming through that environment, right? So yes, it's multi-tenancy, but generally within a line of business, but that line of business can be very large and expansive.
Thank you very much.
All right, thank you.